very much. So this work is basically part of my thesis I did last year. 2 years ago, I actually did a workshop on heuristics, which this was a part of. So hopefully at the end of the talk, I'll convince you guys not to ground anymore, because grounding is bad. That's the takeaway. Right, so the motivation for why I don't want to ground is if you look at a very large domain, for example, here you've got hundreds of trucks, loads drivers, local specs to be delivered. I mean, in essence, not a very difficult problem to solve. But when you use any planner which requires grounding, you die, because you need about 18 gigabytes just to represent this problem grounded. So the question then becomes, what can we do? So this is your typical planning graph for a very typical small domain. But what you see is there's a lot of symmetry in these kind of domains. So in this case, both trucks are in the same location. So the same kind of properties hold for both these trucks. So if you expand your planning graph, it doesn't really care which one of these trucks you take, because both of them will basically get the same properties. If one driver gets one truck, it can also get the other truck, and vice versa. Now, the same holds for the drivers, although not immediately. However, after you allow the drivers to basically walk one step, so driver 1 goes from S1 to P12, and driver 2 goes to S1. At that case, essentially both drivers reach each other's initial state. And from that point on, you can actually treat them as basically identical and become equivalent. And these kind of relationship you can exploit by basically create smaller planning graphs. You don't have to ground. You get still get really pretty good heuristics out of it. And this will actually allow you to solve much bigger problem instances, as we shall see. Right. So what we try to do when we construct this planning graph, or as I'm going to call little planning graph, is to find equivalent objects. Meaning that if you've got an object like a driver who reaches the other driver's initial state and vice versa, and for that point you can treat them equivalently, and you don't need to make any distinction between the two anymore. You can basically combine them together, and this will allow you for much smaller and much more compact representation of the planning graph. However, when you expand planning graph, finding these relationships can be quite expensive, especially if you go back to the first slide. We've got hundreds of trucks, drivers, etc. If you basically compare them pair by pair, it's going to be a really difficult operation. So we want to limit the amount of computation we need to find these relationships. So how do we do that? What we do is we group all the objects which can, in essence, become equivalent. And we basically call these equivalent object groups. Now, how do you find these groups? I mean, the trivial example would be you can just perform reachability analysis by constructing the RPG and basically comparing all the effects in the very last layer. But this will require grounding, and you pretty much build the RPG, which kind of negates the whole point of this whole, not grounding. So what we do is we use a program called TIM, which is created by Derek and Maria, which does similar reachability analysis, but on the type level, not the object level, which means you don't actually have to ground, which is excellent for us. So it performs inference on the type level. So it will basically infer that type structs can be at locations, can be driven around to different locations, drivers can walk about, can get into trucks, can get out of trucks, etc. Now this is a very broad inference, which sometimes is too broad. For example, if you look at this road network here, you see it's disconnected. So TIM won't recognize that all these trucks can never become equivalent because they're part of different road networks. So what we do is we opt to do a limited amount of grounding, but only for these objects, which are either static or, as we call them here, don't exchange properties. If you think back at the SAS plus representation, if you've got an object with a single variable domain, for example, the location, as one, it can only can actually contain a driver or loop, basically a driver can walk away from it, etc. So these are the kind of objects we opt to ground in this representation. So we end up with actions which look like this. So you got drive some truck from location to another location, or some driver board some truck at some particular location. And by basically doing this limited amount of grounding, we can actually construct like very tight groups of objects that can actually become equivalent very quickly. And now we can actually construct a lifted RPG with these actions. And if you look at the number of actions which we construct, you see it's like an order of magnitude less than in the grounded case, sometimes even like more so. So this will cost you like immensely in the memory you need to use to ground these actions. So the question, of course, is like, how do you use it? So if we look at like this very simple example of we've got a simple road network, you got like a truck here, truck there, and like the trucks can move from location 1 to location 2. And you got 2 drivers, and they can walk between these 2 locations. And the goal is to get driver 1 all the way to S2. Now, this is like the initial state, which is represented here. This is like pretty much the same as your general lecture RPG. But after we do, but after we basically construct like a single action layer and construct a new effect layer, you can see what happens. So what happens first is you see both drivers, they can basically walk to each other locations, in effect become equivalent. Then the drivers in this truck can actually get out of the truck, and the drivers over there can get inside the truck. And because this, this actually causes that basically these 2 sets of drive also become equivalent. So now you can see that like in one step, you can actually get like a drive from like P1 into the truck because of these equivalent relationships. And similarly, like both trucks will actually drive to each other locations. And finally, you get that like the driver 3, who's not part of, this not equivalent to any of these other drivers, will now become equivalent because driver 3 can now reach initial state of what was first driver 2, and driver 2 can now reach initial state of driver 3 at the other end by getting out of the truck. So this is now the complete lifted RPG, which only consists like 3 effect layers, whereas in the ground case we actually have to construct 5 effect layers. So there's like a much more compact representation of this of the problem. You can actually construct these like much more quicker as well, as you can see here. So this is like the standard benchmark domains on some of the domains, and you can see on the bottom scale you can see like how much object, like what percentage of object actually make equivalent in the domain, and you can see like if it's a very few objects can actually make equivalents, we do pay for the overhead because we basically need more computation time to construct these lifted RPGs. But if there's like more objects actually can become equivalent, and as the instance of these problems grow, we can actually see that we actually need like less and less time. And trivial examples like gripper domain, where we spend like 80% like less time than like in the grounded case. So this shows you can actually construct these structures much quicker. Now the question becomes, can we actually derive good heuristics from this? So in order to extract a relaxed plan and compute a heuristic, what we do is construct a lifted relaxed planning graph to like the last effect layer, to basically to like level off points, where you can not like construct like any more new effects. And then we can actually use the similar basically similar like algorithm as FF does to extract a relaxed plan from this structure. And we basically use the same same algorithm as FF. So we prefer knobs if available. If there's multiple actions available to basically to reach a effect, we basically pick one which is easiest to satisfy. So in this case, what we want to do is to find the relaxed plan to achieve the goal, get the drive to S2. So the effect, the goal is like basically represented here. And now the question becomes, well, how do we achieve it? So like in the normal relaxed planning graph, we choose an action, in this case only one. So we disembark the drive from a truck at S2. And then we got like 2 preconditions we need to achieve. So the truck needs to be in S2, and in this case, drive 3 needs to drive the truck. And what we can see is that actually these are already present in the initial state. So we end up with like a heuristic of 1, and we're done. Not really, because this is like a very poor heuristic. And this is only because we actually introduce loads of shortcuts, because we group together loads of objects by making them equivalents. But the heuristic estimate is very, very poor. So it's very quick. It's very neat, but heuristic estimate is very, very bad. So what do we do? Now, if we investigate what's happening here, is that we actually substitute objects. So in this case, what we see, we basically want to achieve to get driver 1 to S2, and we execute the action disembark driver 1 at location 2 from some truck. But when we look at the preconditions in the previous fact layer, we actually see that the precondition is that driver 3 is driving the truck, not driver 1. So what actually happens is we basically substitute the driver 3 with driver 1, but because we made these objects equivalent, and we need to account for this by making substitutions to basically get like a better heuristic estimate. So we got two methods for doing so. So one we call the object substitution. So when we find a discrepancy between two objects, so in this case driver 1 and driver 3, we then say like, well, what's the first fact layer where we actually find that these two objects become equivalent, and simply add the number of the fact layer to the total heuristic. Alternatively, we can actually say like, well, the goal substitution is we actually change the precondition to basically reflect that we actually don't want like driver 3 or driver 1 to be in the truck, and add this new goal and basically start again with like this new goal in the heuristic. So in case the object substitution, so things basically, there we go. So in case the object substitution, so we see that like driver 1 is now basically substituted by driver 3. And as we look at like the lifted like spline graph, actually see that like driver 1 and driver 3 become equivalent in the very last fact layer actually. So because the very last fact layer, we simply add 2 to the total heuristic, which makes it a total of 3. So 1 for the action disembark and 2 for the substitution. This is FF, by the way. Whereas FF actually returns a value of 4, so can we do better? Answer is we can. And that's what we do with the goal substitution. So instead of like checking which fact layer become 2 objects equivalents, we actually change the way we look for like a relaxed plan by, first of all, finding preconditions which do not require a substitution. And second of all, if we do require substitution, we add like a new goal by changing the actual precondition. So in this case, the goal is to get drive 1 to S2. So we can look at this embark action, and this time we choose different preconditions, because in this case, drive 1 is actually part of this domain, whereas before we choose one with the drive 3 in it. And similarly, we also need the truck at that location as well. So we basically substitute in this entire domain driver 1, and reflect that same thing in the preconditions. In this case, we see because driver 1 is already part of this precondition, there's no problem. And we simply continue with these two facts which need to be achieved in the spline graph. However, when we try to find a achiever for driving driver 1 inside some truck, we find like a board action, but the preconditions now say that driver 2 is born in the truck, not driver 1. So when we basically do, so essentially what happens is that driver 1 is a substitute for driver 2, which means if you take the this junction, actually find that there's like this domain here actually becomes empty. So what we need to do is we need to change the precondition here to basically say we need driver 1 be at location 1, not driver 2. So that's what we do. So we create a new goal. So we create a new goal, which is actually now says get driver 1 location S1. And we basically find like a relaxed plan to achieve this particular goal, which in this case is simply walking driver 1 from P1 to location S1. And now the final relaxed plan looks like this. So in reverse order, we see we need to walk the driver 1 from P1 to S1, get into a truck, drive a truck, and then essentially disembark. And this is essentially the same heuristic you'll find during the FF heuristic, but you spend less time and less memory to get this heuristic estimate. So in order for the actual planning, so the plan actually built is based off FF. So we use the same algorithm. So we use helpful actions as well. So we try to prune helpful action, and if we fail to find a plan, we basically don't use the action pruning, but basically use a best first search algorithm. And also, an additional thing we do is we try to preserve goals. So when we build the lifted RPG, we try to basically, we remove any actions which could potentially delete any goals which are already achieved. So we don't allow them in the RPG. If we find like a fact layer at the end which achieves all the goal, we continue with that. If we don't, then we basically remove this constraint and build like the regular lifted RPG and go from there. So to show you the results, we basically run like a few benchmark domains, allow 30 minutes of computation, and we compare like our planner using the lifted heuristic with FF, and we can record the number of problems solved and the memory used. So first of all, the results. So there's a few configurations. So the basic case is we use the algorithm without any substitutions, which breeds really bad heuristics. It's very fast, but a very bad heuristic, which actually reflects in like number of problems solved. The object substitution column is essentially we find like the fact layer where objects become equivalent and add that number to the total. And the goal is like if we found a precondition which got like an object which disagrees with like the goals we're trying to achieve, we add like a new goal by changing the precondition. And you can see we don't quite solve as much problems as FF, even though for some problem instances like driver lock and blocks were actually better than FF. In other ones we don't do as well, especially depot. But overall, there's like a pretty good result, especially if you consider like the memory used. So you see that we use like order of magnitude like less memory than FF does. You might be wondering why it's like such like a straight line here, and that's actually because FF essentially like I say allocates loads of memory and only like increase that if it needs to. So what we want to do is what happens if we increase the problem instances by basically making them 10 times big, and see do we actually scale and do we actually manage to solve more problems than FF does, which would be a nice result, and indeed we do. So these are the same problems, but we use like 10 times more objects in these problem instances, and we can see that we scale very nicely, and in top of the row you see FF doesn't solve quite a few problems, whereas we keep on solving them, except for like one rovers domain and 2 satellite domains, which we don't solve, which FF does. But apart from that, we can see that using lift heuristics basically removes a restriction, which is like the memory constraints you have. The heuristic value, which traditionally is very weak using like lift heuristics, now yields like very good heuristics in such a way that you actually can solve problem instances using less memory and more than FF does. And I need to conclude, which is just fine. So in conclusion, for large problem instances, we can actually calculate heuristics much faster than FF does, or any grounded heuristic can. We can augment the lift heuristic by using substitutions, which use very good heuristic estimates. The heuristic estimates are actually on par with the FF heuristic. We use like far less memory. You can actually solve like larger problem instances, and we actually scale better as problem instances become like much larger. And you can actually apply the same method to like other heuristics like this causal graph heuristics, and that's the end. Thanks.
Have you done any analysis on conditions under which you would get exactly the same answer as FF, or how far you can possibly be from FF?
Not exact, but but like in problem instances where you don't find any equivalent classes between objects, you actually do get the exact same heuristic as FF does. So we actually fail quite gracefully. So if there's like no like so if there's like no equivalence you can actually exploit, you get the same as FF does, the exact same heuristic. But when you do, it's kind of hard to say like how close we get to UFF. Sometimes we're better, sometimes we're worse. So it depends actually problem domain. We don't really know exactly.
So I really like the idea of lifted heuristics, but you still need to search on grounded states, right?
Yes.
So have you considered also trying to lift the search somehow, like partial order planning or something like that?
I have considered, but don't have time to actually implement it, but something we do like to do, yes.
All right, no more beer.
Thank you.